Welcome to our webinar in the Frontiers in Healthcare and Information Technology Keynote Series. Today, we are honored to welcome Dr. Jarir Chaar, whose presentation is entitled On the Interconnected Futures of Clinical Neurology, Computer Sciences, and Engineering. And now allow me to present our keynote speaker. Dr. Jarir Chaar is a senior information technology professional with extensive leadership work experiences in automating the lifecycle management processes of highly available complex applications that require large development and maintenance teams working across time zones. His application assembly optimization methodology and its supporting environment, protected by a portfolio of over 50 patents, are widely used throughout IBM Global Business Services and have saved IBM an average of $100 million a year over the last 15 years. So by estimation, this is almost $1.5 billion, which could actually bail out our financial institutions here. Anyways, he recently retired from IBM to focus on building, in partnership with the University of Michigan, innovative technologies that will assist neurologists and neurosurgeons with pre-symptomatic diagnosis and early treatment to slow down or reverse the progress of neurological disorders. And the presentation today will be related to the latter. Dr. Chaar holds a PhD in computer science and engineering and a master's in electrical and computer engineering from the University of Michigan, Ann Arbor. He also holds a bachelor in electrical engineering with distinction from the American University of Beirut. A quick note, Dr. Chaar was my second line manager in Watson IBM. Jarir, the floor is all yours.
Thank you very much, Marcel. I really appreciate the invitation. And I hope everybody would benefit basically from the discussion. I've tried to put a presentation together that is self-contained. So people who are familiar with one aspect or the other of the discussion can upgrade their knowledge basically of other aspects by reading up the presentation without having to go and then search the web, etc., etc. What I would like to say is I'm approaching this topic from a technologist perspective. I'm not basically a biologist or I'm not a neurologist, what have you, but I have built over the years an understanding and appreciation of the roles of the neurologists and neuroscientists and the neurosurgeons, etc., to be able basically to articulate things that are adequate from their perspective as well as feasible from a technological perspective. So with this, let me start basically with the presentation. I'm going to go and try to highlight certain aspects of the presentation, and I'm not going to go basically through every detail of the presentation, but I'll be more than happy also to answer or connect with students later if they choose to, and discuss further any aspect of the presentation they are interested in. So let's start with the challenge. Okay, so essentially, here is the outline. I'll talk a little bit about our challenge here. I'll talk about human nervous system and its neurological disorders and injuries. Particularly, I'll highlight two huge initiatives that have been ongoing since 2013, and they are basically 10-year initiatives, one in the US and one in the European Union. The BRAIN initiative in the US is sponsored by NIH, the National Institute of Health here, and the Human Brain Project in the EU is sponsored by the European Commission. And a total of more than $1 billion would be spent by each one of these initiatives on focusing on trying to understand better the human brain and its illnesses, etc., etc. Then I'll talk about basically some of the disorders and diseases that were a focus. The role of imaging in trying to understand these diseases, the role of neural probes, which are The difference between the two basically is imaging is a non-invasive mechanism to be able to understand how the brain works, while neural probes are invasive. And then, I pose the question, which probably is on the mind of lots of people. At least it's on my mind. Can Lebanon join this revolution? What can we do here, etc.? And what can we, and how we can leverage the fact that you as a team will be focused maniacally probably on this intersection, which is great because it's a good way basically for a country like Lebanon to start moving down this road basically, and then participating in this revolution and potentially benefiting economically as well as technically and academically. Okay, so with this, let's start with it. So we have an absence of sophisticated clustering techniques for assessing the impact of neurological disorders on the brain because these techniques are computationally intractable. They're very, very hard, basically. Why? Because the brain is made up of about 100 billion neurons and 1 trillion glial or glue cells that provide support functions for these neurons. And so when neurons transmit signals among each other, it happens at up to a speed of 200 miles per hour. And when you lose a neuron, you cannot regrow it, basically. When it's damaged or it's dead, it's gone. The typical neuron has about 1,000 to 10,000 synapses. These are kind of the communication links between the neuron and the other basically elements in the brain. So being able to identify the neurons or glials that are affected by a neurological disorder is very intractable because the search space for the root cause and the progress of such disorders still are great scientific mysteries, and they're very, very hard because of the number of connections that are available. So what to do about this? And this is a really question that is being tried, that projects like the NIH and the EU projects are trying to answer. So recent advances hold some promise in this case. So for example, the last decade, scientists have been able really to do great strides in identifying some of the mysteries of the brain. So the sequencing of human genome was one example. The development of tools for mapping neural connections is another big example. Increasing the resolution of imaging technologies. So today, basically, the next generation of MRIs, magnetic resonant imaging, works with magnetic fields up to 7 Tesla. The previous generation was 3 Tesla and 1.5 Tesla. So you have really an increase by an order of magnitude of the strength of the magnetic field in these machines that will generate more precision and kind of more data that you can look at in the brain. Then you have the whole nanoscience basically explosion, which is starting to kind of have influence in certain specific narrow fields of the domain. So we have opportunities here to integrate these different aspects across the scientific field. So take an example. If you combine advanced genetics and optical techniques, for example, you can today use pulses of light in animal models to specifically basically affect the activity of a certain cell of the brain. So you can really control one neuron at a time, basically, with this kind of mechanism. And then another example basically is the use of high resolution imaging, as we just talked, to functionally and structurally connect to the brain basically and study it in humans. So these by themselves basically are examples of the progress that will lead new results, I hope. Okay, so just to quickly go over things. When we talk about the human nervous system, we are really talking about the brain, the spine, and all the nerves basically that connect these control mechanisms of our body basically to our senses, okay, to our, that provide us cognition. And this is kind of a summary basically of how these things are connected together. The spine and brain are called the central nervous system, and the peripherals basically are the nerves basically. They are the mechanisms that control our voluntary motion as well as our autonomic activities that happen without us thinking about things every time. Okay, so these the nervous system is composed pretty much. The brain is composed of cells, and the cell essentially is shown here. The cell has a body which is a soma. It has dendrites which receive messages from other cells. It has an axon that connects it basically and allows it to pass messages between, from the cell body to other neurons, muscles, and glands. And then it pretty much basically is the way impulses are moved between what they call the gray matter and the white matter. So the gray matter basically, in this case, is the cell itself, the cell body, and sorry, white matter is kind of the medium that carries these impulses between to and from the gray matter. So they are the nerve fibers or axons. Okay, so these are very important to keep in mind, essentially, because when you talk about neurological disorders, they affect these elements basically of our nervous system, the cell itself, as well as the gray matter and the white matter. Overall, the brain of a human being is about 1.35 kilogram. Okay, this is the brain itself basically, without the skull, etc. So the elements of the brain are discussed next, and you can see basically that the brain is pretty much composed of the cerebrum. They have two hemispheres, one left and one right, and then each hemisphere controls the kind of the other half of the other side of the body. So our left hemisphere controls the right side, and vice versa. Each hemisphere has four lobes here, and the frontal, the temporal, the parietal, and the occipital. And if you look at on the right-hand side, basically, each one of these lobes has identified with it basically things that it controls. So the frontal lobe controls our movement, intelligence, reasoning, behavior, memory, and personality. The temporal lobe, essentially our speech, behavior, memory, hearing, vision, and emotions. The occipital lobe, our vision, and the parietal lobe, basically our reasoning, intelligence, telling right from left, language, sensation, and reading. And so each one of these elements basically has a role to play. Okay, the cerebellum, for example, in this case, which is located under the cerebrum, is focused on balance, coordination, and fine muscle control, while the brainstem connects the brain to the spinal cord. And so it really helps with breathing, with blood pressure, with heartbeat, and with swallowing. And as also, another view of the same basically shows us essentially what each lobe is responsible for from the perspective of smell in our senses, pretty much, right? Hearing, smell, speech, planning, problem solving, basically motor control, touch and pressure, taste, etc., etc. So as you can see, the brain is a masterpiece, basically, very well organized with key missions for each part of the brain that pretty much are can be the focus, basically, when going deeper into studying the behavior of a human being, and basically the interactions of these different lobes through the movement of blood between different parts of the brain. And this is pretty much what the focus has been of imaging technologies, trying to basically capture this movement of blood between lobes when it comes basically to a certain piece of speech or a certain smell and what have you, etc. Okay, now all these parts when they work right are wonderful. However, each one of these basically is vulnerable to some disorders. These disorders could be structural. Okay, the number of neurons, basically the way they're connected, etc. They could be biochemical, electrical, also, because when they communicate with each other, it's an electrical signal that goes between the different cells. So these can result in neurological disorders that may lead to pain, paralysis, muscle weakness, poor coordination, loss of sensation, seizures, confusion, and altered levels of consciousness. So you can see basically the neurological disorders are plenty to worry about. So these also can be developmental, which means essentially they happen when a baby is being, or a toddler, for example, is developing. It could be psychiatric, it could be neurodegenerative, and most of them basically are chronic. They're incurable conditions whose disabling effects may continue for decades. So the point here is very important. A condition that you might experience at a certain age would have taken decades probably to develop. So, all this, these disorders and what have you, cannot be today detected early on. So they go on in the human's body, and then only basically when they manifest themselves, you can go and then classify them and cure and try basically to manage them because they're not really completely curable. And so it'd be interesting to be able to find out early on about these conditions and find out basically of what you can do to either slow them down, or probably kill them pretty much before they start influencing you on a large scale. So here are examples of development disorders. For example, you have Huntington disease, you have muscular dystrophy that are caused by faulty genes in this case. Psychiatric disorders, you have depression, schizophrenia, post-traumatic stress disorder, attention deficit hyperactivity disorder, and autism, and they are caused basically by brain injury or drug abuse. While the neurodegenerative disorders examples are Parkinson's disease, which is the most complex of all of them, epilepsy, multiple sclerosis, and Alzheimer's disease. And they are caused by the damage or death of nerve cells. Okay. Okay, so this is as far as the brain is concerned. Now, talking about the spinal cord, again, this is one piece of incredible architecture, more or less. It looks flimsy, but it's really what holds us all together. So it's really a cylindrical structure that contains the nerve bundles that carry messages, which are electrical signals in this case, from the brain to the rest of the body. And so, it's composed basically of sections. Each section is responsible for a certain set of activities. They will have 31 pairs of nerves here and nerve roots. 8 of them come through the cervical nerve pair. They start at the neck and run mostly to the face and the head. So the face and head are controlled through the first 8 cervical nerve pairs. There are 12 nerve pairs basically that control the body and extends to the chest, upper back, and abdomen. 5 lumbar nerve pairs, which are focused on the low back, that run to the legs and the feet. And then 5 sacral nerve pairs, which basically also are in the low body, extending into the pelvis. Now, many of these, many problems can happen basically to the spinal cord, many injuries. So you can have basically severe symptoms from spinal and cord damage, which may lead to loss of bladder control or paralysis even. And then these are basically listed here. You can have essentially inflammation in one or more segments of the spinal cord, which is referred to as acute transverse mellitus, cervical spondylosis, etc. So there's a long list here. Basically, I'm going to skip through it pretty much. But the point I want to make here is that in this case, basically, there are a couple of imaging techniques that help you deal with these issues. CT scan and MRI, and I'll talk about them a little later. Sometimes X-rays, basically, and EMG, which shows basically the electrical activity in the muscles of the nerve cells. Similar, basically, imaging also is used in the brain's side. So we're going to go over them quickly later. Okay. Now, how to measure basically the effect on society of all these illnesses and disorders? There's something called the Disability Adjusted Life Year, DALY, which is a measure adopted by the World Health Organization that shows basically, it gives you a measure of the overall burden of a disease, express the number of years lost due to ill health, disability, and early death. And so, sorry, if you take, let's say 2015, the population was 7 billion plus, and the total DALYs were essentially 1,481,000 million, et cetera, et cetera. So as you can see, it's quite a big percentage, basically. So, like if you look down towards the end, basically, 6.39% is the percentage loss of productivity, et cetera, due to, these disorders across the globe, pretty much. And then it's only increasing, basically, as time moves on. Okay, so this is something that might not have had the attention and the focus of cancer, etc., in the old days, but it definitely is something that is forcing itself on humanity to look at very seriously in the future. Okay, so what people have done. The people basically were interested in digging deeper and trying to find out basically how can we model more precisely the brain. Okay, so the NIH initiative, which is called the Brain Research through Advancing Innovative Neurotechnologies, which is basically, this acronym is BRAIN itself, started, it's a 12-year initiative. So there's a paper on the NIH website called Vision 2025, written by two scientists, basically, that kind of inspired President Obama to pretty much focus on the brain and start basically what we have today. So the goal was really to revolutionize our understanding of the human brain. How to do that? First, you have to accelerate the development and application of innovative technologies that can be used by researchers to produce the new dynamic model of the brain. Without tools, basically, you cannot do much. Okay, so applications, basically, interesting, sophisticated tooling, etc., that allow you to manipulate things in a way that it makes sense to you as a subject matter expert are needed. Then you use these tools to produce what we call a new and highly sophisticated model of the brain that can help fill the gaps, basically, in our knowledge today, right? And so you can do this three ways. You can show, basically, for the first time, if you can show for the first time how individual cells and complex neural circuits interact in both time and space, then there is value here. Why? Because essentially, individual neurons are interesting, etc., but they have really to belong to a certain path. So they are able to receive messages and kind of deliver messages or responses. And so being able basically to model basically and show how these cells are interacting with a circuit, in this case, would be very important. This also would go a long way towards meeting the needs of researchers that seek new ways of treating, cure, and prevention, basically, of brain disorders. And it should provide basically an unprecedented opportunity for exploring how the brain enables the human body to record, process, utilize, store, and retrieve vast quantities of information, all at the speed of thought. And this is an incredibly efficient system in terms of the power you use, in terms of the speeds at which you operate, in terms of the decisions you make, etc. That the current basically silicon technology would never be able to kind of meet. Okay, and so this was kind of a focus of the program, and at this stage basically we have 1,100 awards that were given to hundreds of investigators for a total of $2.4 billion. So this is how much the US has spent actually. Fast forward basically and move to the other side of the ocean. The Human Brain Project also was started around the same time by the European Commission. And it brought about 500 researchers together from connecting 140 universities and research centers across Europe to address basically similar challenges that the NIH was trying to address. And what they wanted really to be doing is they wanted to create a software infrastructure, a research infrastructure, basically, a development infrastructure, a prototyping infrastructure, that they dubbed as e-brains, okay, that should allow scientists and industrial researchers to advance their knowledge. So instead of the researcher basically having to build their own infrastructure and waste time basically on something that they really don't understand fully, they will have basically the IT folks business infrastructure and manage it for them. And then as long as they know how to call in certain services that are available through eBrains, they should be able basically to connect to this infrastructure and do their own research. And so what happened, with this initiative is started at 2013, around 2016, basically, it was deemed a failure. And then, so they had basically to redirect it, etc. Today, it's much better, basically, because at least they have eBrains and then something that they will have to figure out, basically, moving forward, how to maintain and support so people continue using it. But also, they had pretty much to redirect some of the projects that were started because the goals of these projects were infeasible or were too optimistic or too ambitious. And so over the last 10 years, basically, for 10 years, I mean, ending in 2023, the EU would have spent $1.019 billion on this initiative, 1 billion euros, sorry, not dollars, on this initiative. So as you see, both basic initiatives are talking about real money. Okay, now what came out of it basically are interesting new domains also that are worth mentioning. So clinical neurology was one of the domains that was a focus basically of these projects. And so it is essentially about diagnosing and treating patients with neurological conditions. It's not surgical, it's really patient-oriented specialty practice in medicine, okay? So the reason they really focused on this is because neurologists used to go by some surveys, they have questionnaires that you fill up essentially, and then they go by what you answer, etc. every time you see them. But the problem is basically that sometimes the details are forgotten or are reported basically in a way that might lead to wrong decisions. And so being able to manage all these artifacts essentially in a way that allows the data to be validated, etc., was a focus. And then you have the key trauma, basically, that was a focus of clinical neurology was the damage caused by traumatic injuries or stroke and mental conditions like Alzheimer's, Parkinson's, etc. But particularly in the US, there was lots of concussions because of the American football. And so, there were lots of money that was put basically to figure out why, these players basically were having these disorders, and then lots of them basically were dying essentially quickly, were not surviving it. And so, this kind of, pretty much dominated the focus of clinical neurology so far. Then there were certain conditions basically that neurology wanted to treat that overlap with other specialties. Okay, so mental illnesses is overlaps with what the psychiatrists do. Stroke, also kind of, overlaps with what the cardiologists want to do, etc. So, there are certain things basically where somehow you needed them to collaborate with other specialties other than compete with them. Okay, now, this is all good. However, there is a role basically that computer sciences has started to work to play here that is undeniable, and then will only basically increase in focus in the future. So with neuroscience as a multidisciplinary area, computer science and engineering were also used to understand brain networks, their connections, and pretty much how the nervous system processes information. And particular process of information is fundamental and fascinating. It's kind of biochemical type of process that happens, mixed with some ability to deliver messages or results basically between neurons using electrical signals basically between them, etc. So this is where kind of the role of engineering and computer science kind of became more and more prevalent. And so also an important piece of this equation is this whole initiative of brain-machine interfaces. And I show some of them basically next. They're really about prosthetics and things that you use basically to ameliorate the vision of somebody, its hearing, its movement, etc. And so these were also a focus whereby you bring together a multidisciplinary team to get things done. Applications from neuroscience were combined with computer science and engineering in order to improve the medical knowledge and assistive technologies to restore neurological impairment. So an example is artificial limbs or cancer cell detection systems through image tracking, or face tracking to diagnose neurological pathologies, or neurorehabilitation technologies and neuroimages, etc. And being able to process neuroimages and then uncover automagically, more or less, basically, what changed essentially a neuroimage that from the healthy state that points to some neurological disorder and what have you. All hard problems, basically, that require some good theory of computer science, basically analysis of algorithms and what have you. Then there was something started that is now referred to as neural engineering in the space of biomedical engineering. This really is about the brain-computer or brain-machine interfaces. Again, basically, it talks about computer-based systems that can acquire brain signals, analyze them, translate them into commands that are relayed back, basically, to a device to carry out the desired action. And so prosthetics, basically, and neuroprosthetic devices are becoming more and more popular and more reliable as we speak. And so I thought, basically, I'll mention some of these prosthetics because they are ways of bringing products to the market and then kind of making basically significant money out of selling them and maintaining them, what have you, that people basically might be interested in doing. Okay, so we start with auditory neuroprosthetics. Sorry. So in this one, they are implants. They bypass a certain damaged portion of the ear and deliver the sound signal to the hearing nerve directly. Okay, so this is where they're different from your traditional hearing aids. So they use a sound processor that is fit behind the ear, and the processor captures the sound signals and sends them to a receiver, which is implanted under the skin behind the ear. And the receiver sends a signal to the electrodes implanted in the snail-shaped inner ear, the cochlea. And so the signals stimulate the auditory nerve and then direct them to the brain. And so the brain interprets these sounds, signals as sounds, and you need really, though, to teach basically the person how to interpret these signals. So there is some significant, basically, training that happens before you are able to use these types of prosthetics. But once you know basically how to use them, they pretty much kind of might be able to get you to feel that you haven't really lost anything from a hearing perspective. This is very important, by the way, and not only for people with injuries, but also for people who are with Parkinson's or people who are getting older and older, because you tend to lose your cognitive senses, and one of the first one to go is the auditory basically capability. So being able to compensate basically by using this one would be a great improvement in the quality of life of the person. Then you have the vision, the visual neuro prosthetics. Again, they restore partial vision function in those who lost vision to disorders such as retinitis pigmentosa, etc. So again, in these devices, basically, these devices include a camera and then a visual processing unit that takes the light and then turns the light into electrical pulses that are transmitted wirelessly to an internal retina implant, and then transmitted to the brain. So there is kind of a path that they follow to get to the cortex of the, and be able to allow you basically to kind of see the object that you're interested in you're looking at or you're watching. Okay. Last but not least is the motor-oriented neuroprosthetic. This is huge in the US, particularly because of after the wars that happened the last 10 or 20 years, and lots of basically soldiers losing limbs, etc. And the government here interested in getting some productivity back out of these injured soldiers, and by helping them basically with prosthetics, what have you. So I'm going to skip the details. You can read it basically, and then move to the next topic here, which is the imaging technology. Here, basically, the imaging essentially, started originally with X-rays and radiation, what have you, but over time, essentially, came MRIs, and which were non-invasive, and then you don't really have to use radiation with them, so they're becoming the preferable way of imaging, except that they're still too expensive compared to X-rays or other basically radiation-oriented imaging techniques. Imaging basically, the structure of the nerve system helps you diagnose kind of large-scale, intracranial diseases, for example, such as tumors and injury for it. And then you have something called functional imaging. And functional imaging are focused on studying the brain functions, okay, by analyzing the data acquired using the brain imaging modalities, such as EEG or MEG, or functional MRI, etc. Okay, so bottom line, basically, I mean, these are very, very widely used techniques. They're probably the best means for us to peek into the brain and see what's happening, even though it's coarse-grained and might not really be good enough, basically. Nevertheless, it's a good start. And so, you are able basically to not only see the spatial resolution, which means the structure and how things look at a certain snapshot in time, but also track the temporal aspect of the movement of blood, etc., between the different vessels. Oops. I lost. Did I lose you folks, or you're still?
You know,
Okay.
the presentation kicked back to the slide.
Oh, okay. You go back, then here we are. Well, perfect.
There we
Thank you. Okay. Good. Okay. So let's talk a little bit about MRIs, essentially. So, MRIs basically are focused on magnets. Okay. So magnets that produce strong magnetic field. And, forces the protons in the body to align with that field. So, what we have really is our body is pretty much water. And so focusing on, the water in our body and then aligning the hydrogen atoms in the water with a strong magnet, basically, is the way these MRIs work. So what you have is when you have a radio frequency current pulse through the patient, basically, these protons are stimulated and spin out of equilibrium, straining against the pull of the magnetic field. Okay, so when the radio frequency field is turned off, the MRI sensors are able to detect the energy released as the protons realign with the magnetic field. The time it takes for the protons to realign with the magnetic field, as well as the amount of energy released, changes depending on the environment and the chemical nature of the molecules. And so physicians can really tell now the difference between various types of tissues based on these magnetic properties. They're trained, radiologists basically are trained to look at the color of these different areas basically of the body and identify essentially whether they're abnormal or they're normal. So, the MRI image, basically, the patient is placed into a large magnet and has to remain still for the duration of the imaging process, which is a painful thing to do. And, sometimes contrast agents are given to the patient intravenously before or during the MRI to increase the speed at which protons realign with the magnetic field. Because the faster the protons realign, the higher the image resolution is going to be. Now, recently, basically, functional MRI is becoming very popular. And so what you have basically is the MRI can differentiate between the white matter and the gray matter. Okay, and it can be used also to diagnose aneurysms and tumors. It doesn't use radiation, as I said before. So it is the imaging modality of choice when frequent imaging is required for diagnosis or therapy, especially in the brain. So if you want really to take images of the brain over a certain period of time, repetitively, etc., your best thing is really to use an MRI because, it doesn't emit radiation and so it doesn't really hurt the patient. The functional MRI is used to observe brain structure, determine which areas in the brain activate, which means they consume more oxygen during various cognitive tasks. It's used to advance the understanding of brain organization and offers a potential new standard for assessing neurological status and neurological risk. It's being used big time, basically, here to look at, the impact of opioids, which are a pandemic in the US, basically. And so, functional MRI is gaining its importance because of the ability to look at the impact, basically, of these opioids on the brain of a certain person. Okay. Now we have 7 Tesla MRIs, which are starting basically to be sold to non-research institutions, basically to hospitals, etc., that also are promising a big deal. So the 7 Tesla MRI offers resolutions which are much higher than the more common 3 Tesla scanners. So this greater resolution should allow the person's care team to identify subtle abnormalities related to their condition. We should be able basically to zoom in on the area much better, basically, that is affected by a certain disease. Or we should be able basically to observe things that would have been pretty much, kind of diluted with the lower power MRIs, etc. And so, this should help improve basically the treatment. And so, examples of things that can benefit basically would be here. Epilepsy, for example. You can detect abnormalities that may be the source of seizures, okay, which is not available today. Brain function, assess functional areas of the brain to plan for complex surgery, including the removal of brain tumors. Okay, you can see basically much more granular the brain, so you don't need to cut basically areas of the brain that are not necessarily, impacted. Aneurysms, more accurately detect basically these very tiny aneurysm basically that generate kind of blood in a certain region of the brain. Degenerative and demyelinating disorders. Again, particularly multiple sclerosis and angiopathy basically would benefit from this one. Trauma and concussion, of course, more accurately detect even the slightest brain bleeding from head injury. And then, you have the vascular malformations also. You'd be able basically to look at abnormal blood vessels in the brain. And so all this basically is good news because in some sense, it allows you to do more targeted treatment to the areas that are impacted by a certain disorder. Okay. Now, I put here also CT, computed tomography, because of its importance for the spinal cord and the bones, more or less, of the person. Okay. So this is one basically that uses radiation. So it's really a computerized X-ray imaging procedure, whereby you have the X-ray basically aimed at the patient, and you have quickly rotated around the body, so it takes pictures. And then every time it goes a full rotation, you have basically a 2D picture of a certain slice of the person basically built. And so there is a mechanism whereby you lower it closer or bring it back, etc. So you're able to kind of take basically as many slices as possible and put them all into a stack of 3D images, and then look at these images basically to figure out the problems. The CT basically, in contrast with the MRI, doesn't do well basically when you have areas which are tissues areas. And it really does best while operating against bones. So what happened is they compensate for this by putting in intravenous, kind of color basically solution sometime before you take your CT. So for example, it's able to capture your blood vessels because it flows through the blood vessels, etc. And then be able to increase the contrast in a way that allows you to be able to see the differences, as opposed to with no contrast basically, where things could be blurred out. Okay, then you have optical imaging, which also holds lots of promise here. And so optical imaging, as opposed to using magnets or radiation, simply uses light. Okay, and essentially there is no exposure to any radiation here. Different frequencies of light are used, infrared, ultraviolet, or visible light. And essentially they are able to monitor the progress of a disease because you can do as many as possible of these optical images, because they don't harm basically the patient. Okay, particularly I want to point out the last paragraph here, which talking about a super resolution microscopy, which encompasses a number of techniques to obtain very high resolution images of individual cells. Okay, so one example is photoactivated localization microscopy, as PALM, which uses individual fluorescently marked molecules to create a super resolution image comprised of a compilation of individual molecules in a cell or tissue. The point here really is optical imaging has enabled scientists to be able to look at the individual neurons. Okay, and so today what we have is people looking at individual neurons these are the neuroscientists. People are looking at clusters of neurons. Basically, these are the clinical neurologists. And there is a gap in the middle, basically, between being able to capture every single neuron versus capture basically enough details of a cluster of neurons that allow you to do something that is more targeted than what we have today. And then this gap needs to be closed and soon. Okay. So just to summarize basically here, if you look at the picture here, basically it shows the spatial resolution in millimeters versus the temporal resolution in seconds. So what you want really the smallest spatial resolution and the smallest temporal resolution. So the fastest basically and the most precise of. So, and you can see here basically there are two types of radiations of imaging, techniques, IEEG and MEG, which are pretty much the best in terms of the results so far. But still, I mean, they're not good enough for doing the kind of research basically that is expected in order to understand in details the brain and its composition. When I mentioned fMRI, which is very well known, as you can see, basically it does good from a spatial resolution perspective. However, from a temporal resolution perspective, basically it's not as good. Okay, you have others basically, but like EEG, for example, which is also very interesting and widely used. EEG, for example, is not good with the resolution, but it's good with temporal resolution. Okay, so this is a good example basically of things that you kind of plotting together on a scale the different approaches, so you are able to identify basically the direction in which you go towards ameliorating these approaches. And also, if you notice, basically the color here shows the invasiveness. So, for example, MEG seems to be very non-invasive, while IEG basically is colored red, so it's kind of invasive. And so, this is also one element that needs to be taken into consideration. Okay, now we're done with imaging basically at a high level. Let's talk a little bit about probes. Probes basically are kind of an invasive way, but very accurate to record activities at the level of a single neuron. So today people use neural probes basically. Neural probes have been around, I would say, since the early 80s, mid 80s, etc. The first one came from the University of Michigan, actually. It was a two probe, it's kind of probe basically two kind of neurons which are next to each other. Since then, they've been developing it big time, basically, and the recent generations of probes are very, very promising. If I go here to the next one, I mentioned two basically initiatives here that are very, very key. One is from MIT, where they designed a protein that tunnels into the outer shell or membrane of a neuron. If there is a slight change in the voltage as when the neuron fires, the protein immediately transforms into a fluorescent torch that's easy to spot under a microscope. Okay, and so they have also a blueprint pretty much that allows basically others to rapidly evolve stronger and more sensitive active probes for the brain. So this is an initiative basically with a new different approach to how you deploy probes, basically how you design them. That is very promising. The next one is about thin and flexible probes that are able to reliably record the electrical activity of individual neurons in mice for up to 4 months. And this one example in particular, basically, the size of the probe really is smaller than that of the neuron. So in some sense, basically, you should be able to easily insert it and then monitor basically the activity of the neuron for a period of time. And so, it could be, for example, that after you do your MRI and you focus on a certain region of the brain, you bring in basically probes and sensors to that region. So you are able to basically kind of zoom in further on the area of that region that is under stress, basically, or unhealthy, and then avoid basically losing some of the healthy neurons around it. So, you know, these techniques basically have to be put together so you're able to get to the end of the game. So with this, I kind of, you know, I'd like to stop here basically and ask the question about how we can, in Lebanon, join this revolution. So I'm going to, just to summarize it, basically, what you have today is you have a big initiative to understand the brain and its composition. And these basically initiatives are going to create what I call a blueprint for the brain. There is a blueprint for a healthy brain. There are blueprints basically for brains that have been hit with different types of diseases and disorders. And so, you know, there'll be also lots of focus on the regions that are going to change because of these disorders. Mapping also, you know, them into that blueprint of the brain itself. The way around it basically is to either, you know, kind of bring more and more power basically to imaging, and or basically use probes, etc. So it'd be multiple mechanisms that allow you to go deeper and deeper into the composition and as well as the you know, structure of each region of the brain, and understand it much more. And so, you know, there'll be lots of tools probably that will be created here, lots of software tools, etc. And so there'll be industries basically that will benefit from this. And then, you know, potentially, in order to advance, basically, you have to advance on all these fronts, and, you know, not be lagging basically in one of them specifically, and, you know, potentially basically try to revolutionize the way we think of the whole, you know, neurology and neurosurgery and what have you, basically. Okay, so for by the way, I should mention also something very important today that is done. It's called the deep brain stimulator. Okay, so for Parkinson's, for example, some people you know, reach a point where the tremors are so bad, basically, that they really need to have things basically calibrated, and they need. So the recommendation basically is to use this deep brain stimulator, which really, you know, lowers a probe in your head, and fine tunes the probe basically to optimize it, so you are able pretty much to reduce the intensity of the tremors or even eliminate them altogether. So this is an optimization problem of the highest degree. And for example, there's a person here in Michigan who made a big reputation for himself doing that by collecting real data from his patients and analyzing them. So they are able basically to compute the location in which they will lower the probe basically in their you know, while treating their patients and what have you. And so, you know, all sorts of techniques and approaches would be needed that borrow from engineering, from computer science, and probably from other domains. And needless to say also that, you know, there is the issue of ethics that is also very important in this space. You know, lots of these techniques basically have to be tried on people eventually before they're being approved. When to try them, you know, when you develop your simulation or you try them on animals, is this good enough? Basically, is the animal brain enough basically to kind of, you know, simulate a certain trauma or a certain disorder, etc. So lots of big questions that have to be answered sooner or later for this space basically to move forward. And then I think personally that given the talent in Lebanon, given the focus that you folks particularly are kind of, you know, pioneering in the country, if, you know, the current situation basically is ameliorated, I'm hoping that, you know, we'll be basically, you know, kind of bringing together groups of people, advisory boards, etc., involving all the Lebanese diaspora as well as the talent in Lebanon, basically, in doing something in this domain that kind of benefits not only our country, but also the whole region. And that put us basically in a position whereby we can create jobs, we can, improve lives, etc., by having people specialize in this domain. And with this, basically, I turn it back to Marcel. Thank you very much for listening. Hopefully, you felt basically that what I proposed basically is, or what I talked about is useful. The rest of the presentation, by the way, is an appendix that has kind of, a very high level, more or less, it defines some or most of the disorders that I talked about.